Hello, everyone. My name is Nick Miller, and my teammates are Diego Briceño, Gustavo Diaz-Galeas, and Precious Grace Brazil. We are Group 11, and we're creating a biofeedback device for our senior design project. So for this project, we're going to be monitoring biofeedback signals. Biofeedback is actually the act of learning how to control involuntary bodily functions just by being kind of aware of them. And so you use electronic monitoring to be able to monitor signals that indicate that these involuntary functions are going on. So some of the common biofeedback signals that we're commonly see are brain waves, dermal temperature, skin resistance, and also heart rate. So for us, we're going to be using this device to help people who have anxiety be able to kind of monitor themselves throughout the day so that as they see that they do have anxiety, they can kind of try and bring themselves down. So the hope is that they're able to reduce the amount of stress that they feel throughout the day. We're actually going to be targeting people that suffer from anxiety and depression and people who have a high stress job or clinical patients. And we want doctors to also be able to use this to be able to see data for their patients. For our project, we had a couple goals, and one of the goals is that it needs to be worn all day long. So we had to make sure that comfort was a top concern for us. For the weight, we wanted to keep it under 300 grams. For the size, it needed to be less than a foot in length so it could fit on the arm. And it needed not to feel extremely hot against the skin for the user throughout the day. We also went ahead and had some constraints when it comes to price, power, and of course, data transmission. Most devices on the market are around $4,000, and we wanted to keep ours under $200 to be able to make it able to be in a lot more hands instead of just a high-end device. The power requirements is we have to be able to go throughout an entire day, so we designed it to be able to run at least 16 hours. And for our actual device, we want to be able to store historical data. So we are sending all data over to the smartphone and storing it there. For our engineering specifications, we decided to make it so that the device must be able to measure the user's heart rate within 15% of a commercial device. We want to be able to measure the skin resistance changes and be able to measure the trends as it changes. And the device must be able to measure the skin temperature within 15% of a commercial device. For the Bluetooth controller and microcontroller, we ended up using the ESP32 in no small part because of the large amount of community support around it. It also was able to give us I2C line, ADC, GPIO, internal flash memory, and it was all programmed using the Arduino IDE, which allowed us to be able to kind of work through it pretty quickly. Another large advantage is that it has a built-in RF antenna, so we don't have to build a circuit antenna ourselves. We looked at a couple different options, one from Cypress, the CYBLE, and also one from Texas Instruments, the CC2640. The ESP32 ended up winning for us because of its low cost and also its strong community support and quite an abundance of libraries and examples. The Cypress was still a good contender because it had a really good development environment. There was a lot of examples, and a member on our team had actually had previous experience using them. And it also included source code for a phone app, so we could have kind of accelerated that part of the project. For the CC2640, the biggest advantage it had was that it was a low power consumption. And we were experienced with the development environment, but the two big drawbacks of it is that we had to use the RTOS, either free RTOS or TI RTOS, and had no built-in antenna. The downside of the ESP32 is it is the highest power consumption of all devices. The microcontroller has a couple different responsibilities. So it needs to be able to pull data from the heart rate sensor using I squared C, and it also needs to be able to control the digital potentiometer through I squared C. It's going to be reading the GSR and thermistor voltages through the ADC, and it's also going to be checking our battery voltage through ADC. And then it needs to be able to send all that data to the smartphone for it to be able to store and display to the user. And we are not going to be doing a lot of post-processing on the device to be able to reduce the amount of power being used. So here you'll see the actual connections that we're making with this device. As you can see, it is connecting to the MAX 3101, which is the heart rate sensor through I squared C and the digital potentiometer, the GSR. The GSR is being read by ADC. Also, the thermistor is being read to the ADC lines. GPIO is going to the battery and charging circuit so that we can actually control it, and the ADC lines are going to the battery and charging circuit also so we can check our voltage levels of our rails. And then, of course, everything is being sent through the Bluetooth lines. For the firmware, we're using the open source Arduino IDE because we found it so much easier to use than programming RTOS. We were able to find community supplied drivers for almost all of our boards, and we didn't have to create a Bluetooth stack or have to deal with a lot of scheduling and being able to create our own functions because we were able to just use function calls from different libraries. When we send this data to the smartphone, we post it up as a single service and as 4 characteristics for the smartphone to be able to read.
Now we're going to be talking about the hardware design for this project. For the hardware design on this project, the main purpose of the hardware is to support the sensor activity for the ESP32. The sensors that currently are on the board are the heart rate sensing, the galvanic skin response, which is the resistance measurements, temperature sensing. But along with those sensor measurements, we also have battery charging circuits. We also have an onboard serial to USB device and onboard regulation. That's more like the different peripherals that we currently have on the board. Let me just go very briefly on the different sensors that we currently have on the board. We have the heart rate sensing, as you could see on the back. We also have the galvanic skin response, which is seen in the red, and we also have the temperature resistance, which can be seen on the blue on the top. Let me just explain more or less what the parameters that we need for the heart rate sensing. And basically, due to the parameters on how we mount the sensors on our wrist, we are limited on how we measure the different responses to stress. One of the key issues with heart rate sensing is that it has to be mounted close to the wrist, but we don't want to do the measurements at the fingertip level. Generally, some optical devices use that device, but also some heart rate measurements can also be done through the ECG or EKG methods. And we were trying to get away from that due to the hardware designs and also the placement for the probes. We will also like to have, like I mentioned before, not just an optical device, but also something that is embedded. They can have both the photodiodes and the LEDs embedded as well. For the different heart rate sensors, we compared 3 different ones. They're with the same manufacturer, and the first one that we looked was the MAX 86141. It's very inexpensive. It's used throughout whole industry. It uses the I2C interface, which is not bad, and also has a very good ADC resolution. It has a 19 bits. It also has ambient cancellation in case like there's some light filtering through the device. The problem is that it uses a BGA form factor and it's hard to manufacture, and it does not have the LEDs on package, so we have to build around it. We also looked at the MAX 86150, and it also has the ambient light cancellation, and it has the LEDs embedded already in the device. They use an I2C interface, but the problem is that it's not suitable for a wrist. It's only suitable for the fingertips since it uses red LED, and also requires a lot of voltages to make sure that everything works properly. So the big middle ground compromise that we found was the MAX 3101. It has the same features as the MAX 86101, 150, sorry, and but it also requires higher voltages, and it's a little bit pricey in comparison. So this is the overall schematic for our device. Like I mentioned before, this is completely configurable in the I2C bus. It has ambient light cancellation. It has LEDs embedded in them, and the only supporting hardware that it needs is just the decoupling capacitors for the rail. It needs a 5-volt rail. It also needs a 3.3 rail for the red LED, and also 1.8 for internal logic. Now I would like to talk about the galvanic skin response. Due to portability and to make sure that the measurements are done accurately, we would like to have the skin response sensors, we would like to have them at the base of the palm. Normally the measurements are done at the fingertips, but we want to make sure that we have enough space that we can actually embed it on the board, but also have accurate measurements. Also, the sensor needs to be able to access an external probe, like I mentioned before, and also it should be ease of programming, and do not use any ECG or AKG methods. We look at different options of how we accomplish the GSR measurements. We look at 3 different options. The first one was to just have a differential amplifier across the 2 probes. One of them was the INA 827, which has a very high rejection mode of 88 dB. It's a very common package, which makes it very inexpensive. The only problem is that it uses a dual power supply, and it needs some further hardware to make sure that the conditioning is done properly. For this reason, we also looked at just taking the differential measurement with a dual channel ADC, which we look at the ADS-121 from Texas Instruments. It's very good because it has a 24-bit resolution, and we can get the data from the flash memory, and it just uses serial input or output. The only problem is that the land area is fairly big to what we want to accomplish, and also needs a lower overhead from the ESP32. Finally, we looked at the LM324, and this is just a simple 4-channel op-amp. It has a fairly high gain of 100 dB, and it's a single supply, so we can just use 1 supply instead of 2. It uses a lot of current draw, but the big kicker here is that it uses the small footprint, which allows us to build more hardware around it without occupying too much on the big board. And like I mentioned before, it's general purpose, so it does not have any special operations for this. Now I'd like to show you the actual final design for the GSR sensor. This sensor originally is the same design that that's used on an open source project called CECS Studio, and it uses a potentiometer or a physical potentiometer. We noticed that in order to calibrate the GSR sensor, we needed to actually hand calibrate the potentiometer, so we added a digital potentiometer in order to make sure that we can calibrate on the fly without having to always interact with it. Like I mentioned before, it uses a quad-up op-amp, which is seen here in the differential configuration. And the beauty of this is it can just use 5 volts and everything's okay. And both chips are fairly small, as you can see on the red square. All the probes are also external to the device. The temperature parameters, we want to make sure that when we measure the temperature, generally for GSR or for anxiety measurements, they use the fingertips. We would like to not use that, so make sure so it's more comfortable when wearing the device. For this reason, we decided to use a thermistor, or something that at least we can extend the probe to the back of the finger at the middle of the webbing of the index finger and thumb. We also would like to have a very compact area on the supporting hardware, so that we don't have to create a big board, since it's going to be in our wrist. And we want to make sure that we avoid overheating due to the current going through the thermistor. Also, we want to avoid thermocouple or junction compensation networks, which can be very extensive and complicated to do as well. We look at 3 different options. 2 of them are similar. They're just built by different companies. The first one is TMP30. It's a TO90 package. It's very stable. It's very linear. But the big problem that we have here is that it's not its own board. So we cannot really make it into a cable assembly that we can actually put in our webbing. And also the LM30 has the same problems. It's also has 3 probes, and also the self-heating is very low. But then again, it cannot be made into a cable assembly. Whereas the USB 1097.5 that has a 10K resistance at room temperature, it has a very high max range, high tolerance, and a low current draw, and it's actually just wired. So we could actually make it into an assembly, but the biggest problem is that it's fairly expensive. Um, Now, let me just show you the supporting hardware for this thermistor. This is just a simple PN switch, very simple configuration. So whenever the ESP sends a high signal, then it will enable the thermistor reading, and it's just connected to 3 volts. That way we can turn on and off the device, and it's not always heating a lot.
Now let's talk about the hardware support. So the other hardware support for this design are as follows. So the green box shows the voltage regulators, which is the 5 volts, 3.3 volts, 1.8 volts. The battery charging circuit, which is the blue box, and yellow box, USB to serial interface. So now let's turn our attention to the power board overview. So we have the battery charger, and it's the input to the boost converter, which will give us 5 volts, and to the LDOs to give us 3.3 volts and the 1.8 volts. So for the power parameters, we need to have it as compact as possible due to we have a limited land area. We also must provide a steady voltage to power the rails 5 volts, 3.3, and 1.8. And another thing is that it should be able to be powered from a lithium ion battery source rather than a stationary charging source. The next one would be the charging must be readily available and accessible as well. So now for the battery charger, um, input to that is the battery, of course, and we looked at 3 different battery. We ended up using the lithium polymer PK cell P503035, which has the rated capacity of 500 milliamp hour at 3.7 volts nominal. And we chose this battery specifically because it is the smallest, it is also the most less heavy out of the 3, and it was the cheapest out of the 3. And we looked at the 2000 milliamp hour and 1000 milliamp hour because in the beginning we didn't know the current draw of the sensors, and we have determined that the 500 milliamp hours was enough. So that's for that for the battery comparison. And the next slide shows us the battery charging circuit, and this is the schematic for that. And the input to this, as I've mentioned earlier, is the PK cell LiPo battery. It also has the 5 volt micro USB input. It charges the system and the battery, and it has the output voltage of 3.4 to 4.4 volts. And we have the programmable charging current for this. Since this charging circuit's output is not does not have a steady output, we're gonna input this to a boost converter so that it is able to have a steady constant voltage of 5 volts. So for the boost converter, we looked at 3 different parts, and this was from the recommendation of the WeBench Power Tool. And we have the TPS 6123, which is what we used. All of the input voltage range and the output voltage range were according to our application. And we just chose the TPS 6123 because of its solid output current, and it is a small size compared to the others. The TPS 63802 was quite bigger, and we ended up using the 6123 because of its price, and it has the feature of the overcurrent and overvoltage protection in the power save mode, which is what we want so that we could have more battery life. So next is the next slide shows us the schematic for the boost conversion. So it has a 5 amp maximum load, 5 volt fixed output voltage, which is what we want, the protection, and a programmable soft start. So the next part is coming from the boost converter. We have 5 volts and we want to step it down to 3.3 volts and 1.8 volts. And we have used an LDO for this. So for the comparisons, We looked at the TPP M0110, which is what we chose in the beginning in our first revision. It is a dual LDO. It has the input voltage range of 4.7 to 5.3. And as you can see, this is a big chip. It is 350 millimeters by 350, and it is quite expensive. It's $6.36. And at the end, we ended up using the TLB 757 for 3.3 and also for the 1.8. It's because we just figured out that we want to make our design more compact and we want cheaper components. So for the ones that we chose, it has an output current of 1 amps and pretty solid 3.3 and 1.8 volts. So in the next slide, it shows us a schematic of the LDO. So it has the fixed voltage output, as I've mentioned, and it is within 1% accuracy, and that's pretty good. It has a low dropout voltage and low quiescent current. It charges the system and battery, and both of the rails are capable of 1 amp output current. And now for the full system integration. What we did, we had the breakout boards, sensor boards, and we were able, after we tested them, we all wanted them into just one board. So we tested all the breakout boards and we incorporated this into just this one single board. So this consists of the sensor, power, charging, the microcontroller, and the embedded RF antenna. So this is a two-layer board with a single connector for battery and external probes.
Now, while the physical device transmits sensor data via Bluetooth Low Energy, a target phone with mobile application that was developed for it receives it. Its general tasks are: one, it receives, processes, and stores sensor data; two, it displays the received sensor data in a way that the user can easily understand; three, alert the user of any changes in their biosignals; and four, display any previous alerts the user has received. Now, in the course of development of this mobile application, there were a couple of situations that arose that necessitated the development of two unique algorithms. The first is an algorithm used in the baseline calibration, where collection of data is done within a calibration period that is started and ended by the user. At the end of this calibration period, the statistical mean is obtained from that collected data, and then a threshold is established for each by encapsulating approximately 60% of all of the received sensor values. The second algorithm developed was the development of a strike system to avoid false positives as much as possible. So the way how this algorithm and system ends up working is that anytime a received value is found to be outside of the calibrated threshold, that is considered as one strike for that one sensor. Once three strikes are reached, a alert notification is pushed to warn the user, indicating from which sensor it came from. Strikes are reset after each pushed alert, or once a counter has reached a specified reset sensitivity in order to avoid false positives. Now, the mobile application ends up exhibiting two different kinds of behavior when it comes to data receiving data from the device. The first is a calibration behavior where when a user is under optimally relaxed and calm conditions, the mobile application stores incoming sensor data. And as it is stored during this calibration phase, it pretty much ends up being used to calculate and obtain a statistical threshold at the end of the calibration phase. And these threshold results are then stored locally on the phone. The second behavior the mobile application ends up observing is a active use behavior, where the user would end up again optimally begin at a relaxed and calm condition, where as the device is warned by the user, the mobile application ends up storing the incoming sensor data, and as it's being received, it is being compared against the threshold values obtained during the calibration phase. If the received sensor data is found to be within the threshold, then no alert will be pushed as the user is obviously in a relaxed and calm condition. However, if the received data is found to be outside the threshold, that is one strike against that sensor, and once that sensor accumulates a third strike, an alert is pushed to indicate that the user is under a stress condition. Now, the mobile application was developed for the Android platform, done in Java within the Android Studio development environment, with a target of Android 5.0 and above. And the mobile application also ends up making extensive use of a custom Bluetooth Low Energy API that ended up easing and accelerating the development of related Bluetooth Low Energy features of the app. So during the development of this Android mobile application, two phones were used. The first was a Motorola Moto E4 Plus that has Android 7.1 installed, and a Motorola Moto G7 Play, which has Android 9.0 installed. Now, the overall breakdown of the Android application can end up being described as being composed of two principal Android activities. The first is the dashboard activity, and the second is a notifications activity. The dashboard activity ends up displaying sensor values as it's being received in real time, and they do update accordingly, and also allows for that calibration behavior through the press of a button. When this button is pressed, it'll also give the option to end the calibration. The notifications activity ends up storing all of the alerts that were pushed to the user, while also indicating from which sensor it came from, and also including a timestamp showing from most recent to least recent.
So during our project, we encountered some problems and difficulties. Obviously, the COVID-19 outbreak kind of caused a lot of troubles. We weren't able to get to the college to be able to use the lab resources. And also, we had huge delays from ordering parts in China. So initially, the serial to USB did not work, and we could not debug it because we didn't have lab access. RTOS programming for the TI microcontroller was found to be too time consuming. For our mobile app, the backend BLE functionality that was native to Android Studio was lacking, and it took us quite a bit more time to kind of work through that. And of course, we've had a lot of supply chain problems when we were ordering both boards and components. So for our project, we have our estimated costs versus what we actually end up spending, and almost in every single category we came in under budget, and overall we came in way under budget. Our biggest cost was assorted electronics, so these are all the parts that like resistors, capacitors, IC sensors, connectors, such and so forth. The printed circuit boards, we ended up having to pay a little bit extra because we had to go domestic instead of international with these. And we also had to pay for expedited shipping, which is part of our unforeseen expenses. So for the team responsibilities, we broke it up into the computer engineers and the electrical engineers. The electrical engineers handled a lot of the actual electrical engineering of the boards, while both of the computer engineers handled a lot more of the software side stuff. So Diego handled most of the sensor wiring, and also the RF side when we were originally using the TI microcontroller. Grace went ahead and handled all of the power circuitry. So this is charging, DC-DC conversion, everything in that boat. I handled the microcontroller firmware, so that's all of the management and all the reading of sensors and any kind of communication. And then Gustavo handled the phone side of development, so the app itself, the wireless communication, the BLE, handling notification, and everything that. I will say every member of this team actually did work in almost every other part of this, but these were our main areas of focus. So thank you so much for watching this presentation. Thank you for being a part of our committee. We really hope that you enjoyed it, and we look forward to any feedback that you may give us.